Welcome to Ask and Learn.
A cubic function is a polynomial of degree 3 of the form f of x equal ax cubed plus bx squared plus cx plus d, where a is different from 0. In part A, we will show that a cubic function can have two, one, or no critical numbers, and we give examples and sketches to illustrate these possibilities. Part B, we discuss about how many local extreme values can a cubic function have. So in part A, we're going to start by remembering the definition of critical point. And we know that C on the domain of the function is a critical point of f, or a critical number, if the derivative at that point does not exist, or it exists and is equal to 0. So this is the definition of critical number we are going to use. And so, first of all, we know that the domain of a cubic function is the real numbers, the set of real numbers. So if f is a cubic function, then the domain of f is the real numbers. That is, the function is defined at every real number. That is because a polynomial is defined everywhere for any real number x. We have this, and then the derivative of f is given by, we have to find the derivative of this general expression here, is 3ax squared plus 2bx plus c. And we know from the statement of the problem that a is not 0. If a is not 0, sorry, here I made a mistake, it's 3ax squared. Sorry. So because a is not 0, this term is not 0, and then it's a polynomial of degree 2. But before saying that, we can see that this derivative is defined everywhere, that is for any real number x. It means that this possibility is not an option in this case. So we can say that f derivative is defined at every real number x, and the conclusion of that is that the critical numbers of this function, this cubic function, are those real values x where the derivative is equal to 0. The only critical numbers are those values x in the real numbers such that the derivative of f at x is equal to 0. That is because this option in the definition cannot happen in the case of the cubic function, because the derivative is also a polynomial, in this case of degree 2, and is defined everywhere in the real numbers. So the only possibility for a value x to be a critical number of the cubic functions is that the derivative at that point is equal to 0. And it could be any, in principle, can be any real number, because the domain of the cubic function is a set of real numbers. So we gotta find this equation here. But the equation f derivative equal to 0 is the same as, is equivalent to the equation 3ax squared plus 2bx plus c equals 0. And we know that with a different from 0, this equation has 2, 1, or 0 roots. Then can have 2, 1, or no roots. Okay, so if we take into account what we said before, it means that the function f can have 2, 1, or no critical numbers. Here I put this way because we can have 1, so in that case it will be no root or no critical number. So this is the situation. We have a cubic function. That cubic function is defined everywhere in the real numbers, and its derivative is also defined everywhere in the real numbers, and so the only possibilities for critical numbers for this function are the real values of x for which the first derivative is 0, and this becomes a second degree equation which we know can have 2, 1, or no roots. And then this implies that the function can have only 2, 1, or no critical numbers. So let's put some examples of that. So I'm going to take first the function x cubed minus 3x squared plus 2x, which can be factored out as x times x minus 1 times x minus 2. It can be verified easily that this is a factorization of this function. And the derivative 3x squared minus 6x plus 2 has two different real roots. So in that case, the function have two critical numbers. And the graph of this function with three real roots, x equal to 0, x equal to 1, x equal to 2 is this one here. And as we can see, we have two values of x for which the derivative is 0, about this point and about this point here. So this is an example of a function having two critical numbers. One of them corresponds to a relative maximum value here, and the other corresponds to a relative minimum value here. Another example is, and I highlight here that this case of two critical numbers corresponds to two roots for the first derivative. That is, if we find the first derivative of this function, 3x squared minus 6x plus 2, we can see easily that that derivative has two different real roots, and these two different real roots corresponds to two critical numbers of f. So another example is x cubed. So let me put here two critical numbers. Now x cubed, which derivative is 3x squared, which has only one root, which is in fact the same root as x cubed, which is x equals 0, has only one critical number, 0. Let's see, x equals 0. And in this case, if we draw the function x cubed, we get this graph here. And as the derivative represents the slope of the tangent line to the curve, we see that at 0 we don't have a relative maximum or minimum of the function, because the function from one side to the other of 0 has negative and positive values respectively. So it is not a maximum or a minimum. But the tangent line is just the x-axis at 0, and so that is why this graph, which is always increasing, has some kind of flat appearance near 0. Okay, so in fact the root 0, x equals 0, is a third order root, because it's a 0 for the function itself, a 0 for the first derivative, and also a 0 for the second derivative. So it's a third order there, 0 of the function. But in terms of relative extrema, it's not a relative extrema at all, but it is one critical point, because there is only one root for the first derivative. And the other example we will show here is f of x equal x cubed plus x, which is the same as x times x squared plus 1. The first derivative is 3x squared plus 1. And this corresponds to no critical numbers. And that is because this expression here is always positive. X squared is positive or 0, times 3 is positive or 0, but when we add 1, it's strictly positive, so it cannot be 0. So the first derivative has no real 0, so the function has no critical numbers. And if we draw this function, we can see that we have this situation where, because the first derivative at 0 is 1, we don't have this flat appearance near 0 as in the case of x cubed, but we have some kind of slope here, which is just a slope 1 at the origin. So the function don't have real extreme values at 0, but it has not the flat appearance near 0. But again, there is no extreme value, and it corresponds to non-critical numbers. It's very important to notice that in cases 2 and 3, that is x cubed and x cubed plus x, we have no extreme value, but in the case of x cubed, we have one critical number, which is the only root of the first derivative. And in the case of x cubed plus x, we have no critical number, because the first derivative is not 0 at any real number. And that are the possibilities. And now we have already almost give the answer to part B, and that is we can only have two extreme values or no extreme values at all. So a cubic function can have two extreme values that corresponds to the first derivative having two different real roots, and in fact, one of these critical numbers corresponds to a relative maximum and the other to a relative minimum, as in this case here above here. And that's one possibility, but the other possibility is that it has no string value at all. And there is no other possible way because in the case 2 and 3, that is one critical number, no critical number, we will always have an inflection point that is a change of concavity, from one side to the other of the point. Three string value having two different roots, or it has no string values at all. So these are the possibilities.